All right. Before we get going, let's do it. All right. I think we got critical mass, so let's do it. It's my pleasure to introduce today's Colloquium speaker.
It's been a minute.
Yeah.
Almost 20 years.
Exactly. So, super thrilled. It's been super great to have him here on campus for the last 6-ish years. We're trying to figure that out. And we're here a little bit today about some of his work, and we'll go from there. So thank you, Paul.
Thank you. Thanks for the nice introduction. Thanks for coming. It's great to give an update about what I've been working on, because I did give a seminar here, 2020, on topics related to the regional climate of the Northern Plains. And what we've been working on lately is an acronym invented by Encore, Advanced Baseline Imagery Live Imaging of Vegetated Ecosystems. And this is an interpretation of the carbon and water cycles from geostationary satellites that integrates machine learning and is integrating meteorological data and is trying to do more and more and more. Now, I'd like to thank a number of people here, kind of the team, Danielle and Sadegh in particular, Avanti, Sophie, a lot of people, including Encore, and some colleagues at Princeton, Einar is now at Penn, who have provided some key data sets that have helped out, as well as funding from UW Research Forward, NSF, USDA, and lots of data. So a lot of things that we kind of come back to in our field lately is a quote by an eminent scientist, Dennis Baldacci, who just retired from Cal Berkeley. And I know he's said it many times, but he was hosting kind of a relatively large workshop in Berkeley. And he said, we need to measure fluxes everywhere all the time. By fluxes, he means surface atmosphere, carbon dioxide, water vapor exchange, heat, and the other things that we measure with eddy covariance. And people in the audience were kind of chuckling. And I thought, I think we can actually do that, right? And it just is going to take a little bit more than how ecosystem scientists, like perhaps myself and perhaps Encore, depending on what hat we choose to wear, how we think about science fundamentally. And so in the carbon cycle world and in terrestrial ecosystem science world, we oftentimes look toward the past. It's very important. Key to understand the past, understand these processes, understand the Earth system. Look at these fundamentally critical time series that are somehow now at risk, like the Keeling curve. And then we kind of project, and when we project, we do it way out to the future and try to see what our models do, out to where we can make some steady state assumptions about the climate system, quasi, 2100, and see if the models are all diverging, and then wonder what's happening. And this is good. We're trying to know kind of what's happening and why. But then we kind of we sometimes in ecology say physics envy, but maybe it's really meteorology envy, where if we're trying to see everything all the time, we need observing systems. And we need what you have. We want to be like you, right? We have, this is an image just of smoke in the high resolution rapid refresh. We have the geostationary satellites that I was going to talk about, right? We have Zeus, the god of weather. But can we put together that past information, right, and the present knowledge and observing systems? Is this related to making a digital twin, sometimes people say? And then also look toward the future, right? Can we do that well? Or are we making a three-headed monster that we can't control? Or, like I'm probably doing, are we doing one or two things well at the expense of doing the other thing well? Okay? Can we do it all at once? And my answer is, hopefully, but it's going to take some doing. So, we might have a solution here, a little bit. In this building that this person helped make is an observation system that allows us to see ecosystems like we see the weather and forecast ecosystems like we forecast the weather. Right? So Werner Suomi, I'm grabbing this is straight from Wikipedia, and there's a talk that I gave at the University of Minnesota a couple of years ago to point out that he's from Minnesota. But, right, eminent University of Wisconsin scientist who was critical in helping us have some of the absolute first true color images of Earth. True color meaning red, green, blue, okay? I do want to point out that the 50th anniversary of the GOES satellite series, whose genesis in many ways, of course, came from ATS. Many of you here know so far much more about this than I do that I shouldn't really be talking about it, right? But it's in a couple days from now, in this room, with our wonderful accent wall, moved from 351 because we're having class, we're having bioclimatology class then. I want to take everyone And then I thought, let's just have it in this big, wonderful room. So if you're free on Wednesday at 11, there's going to be an SSCC seminar about 50 years of GOES here. Or you can join it online. Okay, so this is red, green, blue. But then for decades, actually the GOES mission didn't observe in both the visible and the near infrared, right? Or it just measured one channel in the visible with their multi-channel sensor that only had 5 channels. But then we kind of, right, can come back to the future with GOES-R, especially the advanced baseline imager. And we are now measuring many channels in the visible, near infrared, thermal infrared. And as it happens, a lot of those imagers, I know this is a little bit tricky to see, it's a figure from my colleague Joel in a paper that we published by former student Anam in 2021. It sees things that are related, right, in their spectral sensitivity to the satellites that terrestrial ecosystem ecologists usually use, like Landsat and MODIS, right, these polar orbiting satellites that we use to create estimates of the carbon cycle, water cycling, vegetation structure, and function. And we do so, and as soon as NASA's back up and running, I'd like to point out that this needs to be in a slightly finer digital format, right? It makes things like simple vegetation indices. Okay, the absolute most simple, and you can argue about its use, it's very useful, sometimes there's better ones, is like the normalized difference vegetation index, right? So reflectance in the near infrared minus the visible divided by their sum. And this is because in the near infrared, vegetation reflects very strongly, and healthy vegetation absorbs very strongly in the visible. So the difference tells you something about kind of how many leaves there are and gets toward how good those leaves are doing. So now, right, and so dead vegetation is going to reflect less than near infrared, is going to reflect more in the visible, okay? So this is going to give us a lower NDVI. These basic vegetation indices, you need visible and near infrared to do so. And GOES can now do that, and it's been doing it a long time. As a consequence, right, GOES-R series can basically not just see the weather, but it can see ecosystems if we're applying the right approaches for atmospheric attenuation and more. So, what are we doing with ALIVE? Okay, we're taking eddy covariance observations from ecosystems around CONUS and beyond. We're integrating those with GOES-R data products, and we're creating some data products of our own. And now, and just recently, at least my water flux estimates will have the high resolution rapid refresh ingested into it too to add some surface meteorology, all brought into the machine learning algorithm to create ALIVE. So the irony about ALIVE is it's supposed to be like real time with the daily latency. But this is actually from last Tuesday because it hasn't updated for a couple of days. I don't really know why. So this is what ALIVE looks like, right? So this is last Tuesday's, not yesterday's, estimate of photosynthesis. Okay, canopy carbon uptake from by ecosystems all across, right, the CONUS field of view. You can see it was a lovely day in California. It was a lovely day in Cuba. You can see, if you look in closely, some really cool features. You got to wait for the sun to rise again. This is all in UTC. It's October. The sun is, oh, it didn't update again. Oh, what's that? That is PowerPoint thing. Okay, now it's updating. There's a lot of cool features that you can see. Okay, if you're having US-made sugarcane sugar, that's right here in Lake Okeechobee in the big sugarcane fields. You can see that across much of southern Wisconsin and places, the corn has been harvested. Northern Wisconsin actually has a bit more carbon uptake. Right, you see it was a gorgeous day down south. You can see the weather systems moving through that are impacting the radiative environment, that impact the ability of ecosystems to take up carbon. Making this, right, took a little doing, and we're trying to always make it better and better. So for example, there's some basic and very well thought out data products like for downwelling shortwave radiation and land surface temperature that are products from the GOES-R series. We've kind of created our own using different types of models, right, either LSTM models or gradient boosting models that use the surface observations to make these predictions in kind of an empirical machine learning way as a contrast. And then all of this is built into a workflow, a relatively complicated but ultimately achievable workflow that takes data. It actually takes data from Google Cloud Storage, not from the building here. It takes the top of atmosphere bands and it takes the surface reflectance bands, right? There's a machine learning model that and also uses those to create models for shortwave radiation, land surface temperature. Uses these to create some novel vegetation indices that also include the shortwave infrared that's related a little bit to water. Not exactly sure why, but it works better. We bring all those things together in a machine learning model, and for which we've been using gradient boosting, extreme gradient boosting. It just seems to be the fastest and not the worst. So it's like an order of magnitude faster than a random forest while having about the same predictive skill. The thing that we're doing that I'd like to point out is not all of this kind of modeling, right? But rather that what we're doing, in effect, is we're adding our new arrays, our new predictions, to a growing zarr library. And the way that this is working, right, is the zarr library has metadata appended to it using a service called Array Lake. That's from a company called Earthmover, but the engine was called IceChunk, and IceChunk is now open source. So it's now an open source metadata provider for your zarr array data that you can add, right, to your zarr libraries, and then they like to live on the cloud, right, a cloud native data format where you can put them back in a bucket. We use something called Tigris object storage S3 buckets, which is just a very cheap S3 bucket. And then from there, right, we have our services that you can use to work with the data. You can just use it all with Colab in Google, Python code, and it's relatively straightforward to use when we have all of our lessons. But I really want to say this isn't necessarily the solution to the world's problems, right? But for something that is so temporally dense, and you want to also perhaps understand something about the time series for it, right? The zarr format, I think, is a great way to go for adding to and communicating those data sets. So with that, like, what can we do with Alive? Okay, one of the big motivations for this is that life and death both happen fast. Okay, there's rapid changes in phenology, right? Like the corn growing, especially this summer, it grew gangbusters. There's flash droughts that happen, right? And people here in the building are studying those very well all the time. There's, of course, extreme weather events, right? There's, I don't know, all sorts of things that happen, extreme weather, biologic agents happening, fire that's happening. And we can use Alive to see what's happening in real time, and we can use Alive to interpret these changes. And also critique Alive and critique the other types of data products that are around to see if they are accurately capturing how things, like in this case flash drought, is impacting the carbon cycle at regional scales. So what's this, right? This is a depiction of a study of a flash drought of a few years ago that really hit sort of the south central United States with a focus on Arkansas and Oklahoma, also a bit of southwestern Missouri. And this was a quick change, right, in the US drought monitor from something that was relatively well watered to relatively bad drought in the course of just a few months. We're talking here between late June and late July. So over the course of just 1 month, we saw a big change in dryness, and we saw our Alive predictions, right, have a relatively less strong change, right, in carbon uptake over time, but it was able to find it very rapidly. So this kind of changes perhaps our, compared to the MODIS product, which is only 8 days, right, and compared to colleagues who gave us a product from their Breathing Earth System simulator, which happens every 1 day, but we had to ask them to run it to update it to 2021. This is the point I'm trying to make. MODIS is like every 8 days. It's pretty good. It's kind of up to date, right? Other carbon cycle products, this is daily, but it's from a few years ago. I think it's almost like I missed a meeting where every single carbon data product just like has to end in the year 2020. And if I had a nickel for every carbon cycle data product that ended in the year 2020, I don't know, I'd probably be able to pay off my mortgage more quickly. So there's just a dearth of information in like near real time about how carbon cycle processes work. And we're trying to fix that. And there's also dearth of understanding of how extreme events impact the carbon cycle. So these are just static images of Alive's estimate of what happened during Hurricane Ian, right, from 2022. Okay? Gorgeous day beforehand, right? This is a few days beforehand, right? Look at how nice things were in Cuba. Okay, the hurricane is now here, right? You can see the darkening skies are causing a lessening of your carbon uptake across all of southern Florida. We have it hitting here near Fort Myers, right? That might be toward the eye of the hurricane. But there's, right, throughout this area now, then we see this now, it thinks it's recovered. And this area here, of course, is all cloudy. And now the hurricane passes, and you can see the Carolinas starting to decrease their GPP, and it's hitting here again in South Carolina, right, with relatively low carbon fluxes. And then, kind of a period here with like less carbon uptake, right? So we're able to kind of figure out, and there's a challenge with these extreme events, is that they tend to knock down at ecovariance towers, or at least damage them quite a bit. You can't really go that readily and just with your chamber system or whatever to measure fluxes after a hurricane, because there's probably other things you want to do after a hurricane than race out to the Everglades and measure your carbon fluxes. Right? So if we're able to see and interpret how these things are changing at large scales, we can learn about how extreme events impact biology at like a large regional, right, scale than you would have from any other type of observing network. Kind of what we found, of course, like right by the eye of the hurricane, there was a decrease in carbon uptake, right, with trees being knocked over, leaves knocked off of trees. But for the most part, especially inland, as soon as those winds were not quite so strong, for the most part it had a beneficial impact because it brought quite a bit of water. Okay. So immediate damage, but as on the measure, right, not too bad impacts on the state, even though this was a particularly bad hurricane in many regards. Yeah, question?
Go back for a second. How much of the decrease you see that's on the 28th at, I guess, 1800 UTC, of the upper right image, is that just due to cloud cover as opposed to any other?
Yeah, this is all due to cloud cover. And so we have some time series analyses that I'm not showing, and maybe I should have, for really how everything recovers like afterward. Right, so there's kind of immediate decreases in GPP, but it really a lot, when we made our maps, and I could show you the map, it's in the paper. This was published by Danielle Losos and others just a few months ago in Remote Sensing of Environment. When we're comparing our maps against each other, you can see really pretty bad impacts, really right along the fringe of the coast. And for the most part, elsewhere, not particularly bad. And that, interestingly, had a little bit to do because there's quite a lot of agriculture right here. Right, and so kind of short, scrubby ecosystems, nothing too tall. So the damage wasn't that bad. Yeah.
So is the Alive product, I'm just trying to understand what it's actually showing, or what it actually is. Is it a diagnostic sort of instantaneously, or is it predictive?
Oh.
A few hours ahead, a few days ahead?
Oh, that's where I want to go. This is excellent foreshadowing of the rest of my talk, because right now it's meant to be right now. But I want it to go ahead. But ecosystems are a little different than the weather, and we're still kind of writing grants and thinking about the best ways to do that. But it's awesome foreshadowing of where we're going. Because the other place we're going is that we were presenting like these kind of 5-minute estimates of everything. And that's a little bit of a bear just for too much information when it comes to understanding carbon fluxes like every 5 minutes. We don't measure them that quickly. We're kind of stepping back to an hourly interpretation, in part to link to the HRR, the High Resolution Rapid Refresh, which is going to soon be the RRFS, perhaps, the Rapid Refresh Forecasting System. And I know that these products are, in many ways, right, not perfect, no product is. It's kind of the best that we have for like a kind of real-time, like near-surface estimate of the meteorology, surface meteorology across the US. And perhaps there's a better one to use too, and then we'll try to plug it into Alive. So while we're doing all these things, right, we need to step back and say, in our field often, right, Martha Anderson did it 20 years ago. So Martha here, for a long time, with Jason Otkin and other people who are in the building, guided in many ways by John Norman and others who, Emeritus Professor of Soil Science here, George Dyack, you see his name on papers all the time, have been using geostationary satellites to estimate carbon and water fluxes for some time, right, even before the GOES-R series came, when they're using the thermal imagery to understand something about evapotranspiration, and then coupling that water flux to carbon flux using mechanistic models. Right? So there's still a lot of legacy in doing this, but no one had really been doing this in the new GOES series. But the things that we're doing are mostly just empirical, right? They're taking eddy covariance observations and saying that this is what this pixel is doing at this time and let the machine figure it all out. But we want to also be guided by the knowledge of things that we know about how ecosystems work. Not just say, okay, here's a bunch of data, the computer digests it all and gives us an answer. Right? This is nice from like maybe an engineering perspective. It gives us something tractable, we can add uncertainties, but we want to understand something more about underlying mechanisms. Right? We want to see if we can take these types of data products a step further to also ask questions, right? To ask questions about how ecosystems work, and ask questions about what can we extract, what information we can extract from our knowledge of ecosystems to apply to larger scale inference. So one way that we're using knowledge-guided machine learning, and this is mostly the work of Sadek Ranjbar, who's a postdoc now in lab, is to estimate a really difficult to measure term. And this is from a paper we wrote a few years ago, but it's this term, sorry the font is so small. This is the evaporation from intercepted water. Right? This is dew evaporating. This is after rain, the canopy being wet evaporating. This is water that's not going into the soil to enter the roots to leave via transpiration. This is a hard measurement to make. You can measure this using a technique called sap flow. You can try to measure it right, by putting chambers over leaves. We don't know enough, in my opinion, about how water enters the atmosphere. And I have a fundamental thing to know about. We do know a lot about how all water, right, enters the atmosphere via evapotranspiration because we can measure that using eddy covariance and other techniques. Right? One thing that we're doing and working with colleagues, right, this is Ainara Zahn, Vegetated at Princeton, now she's at Penn, starting a faculty job, is this notion that in eddy covariance we have a lot of high frequency, 10 hertz, 20 hertz observations, and there's information in all of those eddies. Namely, if you have a little eddy that has more water vapor and less CO2 than the surrounding air, right, that must have been an eddy that interacted with a leaf or something that is releasing, right, water to the atmosphere via transpiration and taking it up via photosynthesis. If you have an eddy that has more CO2 and more water vapor than the surrounding air, that is something that is respiring, right, like you and I are doing right now, and also evaporating. So you can build up time series that kind of parse out where the water is coming from using different approaches, but it still doesn't tell us about this interesting question about how much is coming from the plant through the stomata, how much is coming from the surface of the plant, and how much is coming from the soil. These are hard things to figure out. What we're doing, and we're also applying this to some carbon cycle principles, is giving a transformer type method some rules and say, okay, this is total evaporation, this is total transpiration, these two things have to equal evapotranspiration. We can't have intercepted rain after 24 hours after rain, it must be dry by then. Let's just say 8 hours after dew, the grass is probably dry. Maybe it isn't, maybe it is, not really sure. Perhaps relatively conservative. Right, have some physical rules about how all these things work, try to figure out where we extract the intercepted rain from, and then come up with models, right? Come up with models for how much of our, I'll probably show this one, right? Water is coming from evaporation, that's intercepted, right, which is usually 0, but sometimes non-trivial. How much is coming from transpiration? This is a histogram of the flux as a function of the probability of the flux, and how much is like surface evaporation, right? So we can see, we can kind of add some more mechanistic insight into water cycle science, ask the machine some questions about where it thinks the intercepted water is coming from, right? And build those types of things into our real-time estimates, not just of total water flux, but where the water is coming from. This might be helpful for understanding irrigation. It might be helpful for understanding the impacts of changing storm systems on water fluxes back to the atmosphere across the United States, and therefore how those changing weather patterns are impacting plant physiology. Asking the question, is it going through the plant? Is it not? So going forward, right, we're trying to build more and more knowledge-guided machine learning. We're trying to be less empirical and more fundamental while still relying on machine learning, while still relying on artificial intelligence. And we're trying to find applications including yield and drought forecasting, right, predicting when canopies are going to rapidly change. We're also trying to get more high resolution. Okay, this is because GOES out in geostationary orbit about more than 35,000 kilometers away. The pixel sizes is 500 meters at best. We use a lot of data products that are 2 kilometers. People nowadays want everything. They want it all. They want high spatial resolution, they want high temporal resolution, they want high spectral resolution, but they can't get all that stuff, right? So how can we kind of downscale GOES to be at more of like a management relevance spatial scale in the order of 10 meters? And also, we're only looking at the GOES, CONUS, and Western Hemisphere view, right? Can we stitch things together for a broader interpretation across more of the world? And so we're working with our colleagues at NASA on this GeoNext program, where they're taking like the Fengyun and the Himawari, also GeoComSat, the different geostationary satellites that are over East Asia. Right, goes over the Pacific, goes west, goes kind of right over the point where Ecuador and Colombia and Peru come together. Right, so now goes 19, used to be goes 16. Right, we're looking here. And then over Africa, Europe, West Asia, they just, as of a few months ago, have Meteosat, is it 12 or 13? It's 12, sorry, I think it's a typo. Where they had the MTGI-1 sensor not operational yet, flying for a number of years before they just started sending imagery. So we can now sort of stitch together this critical part of the world as well as we can stitch together these parts and try to build an observation system that is a little bit more coherent across everything. And now it's time to answer Michael's question, right? How do we predict future fluxes? If we have this type of workflow, which again is a bit of a bear, and we have added, right, our high resolution rapid refresh and things like air temperature, soil water to our model. Right, we're predicting now carbon dioxide and water vapor fluxes. We're working on predicting uncertainty. Okay, all of those things can be added to our array, but how do we forecast? Right? And this is really my question to you. There's amazing weather forecast products, and I'll show you a few, and you know that more than I do. But how do we reflect what the land surface is doing? Do we want to forecast these fluxes like directly as the changing variable, or do we want to forecast like the state of the ecosystem through a forecast of their reflectances in the visible and near infrared? Basically like a forecast of how the ecosystem is shining light back that is coming into it. Like, how do we do that? And then once we do that, this is where zarr gets cool. So we can think of ice chunk fundamentally as being like Git for data. So what it can do is it will just commit as soon as we make an actual observation in real time of a quantity and make a prediction, it can commit that new layer to replace the prediction that had been made. Right, we just Git for data. We're just committing new data using ice chunk into our zarr library. And we're creating a system where we can see the future and have also, real time, this is answering our three-headed monster question, while also going back and seeing the past. Okay, because these zarr libraries, they're not like geotiffs, they're not individual files. You can chunk these things to be able to access the data in space, which is like this, which they call lasagna slicing. You can look at it in time, like a pixel and how it's changing over time, which they call spaghetti slicing, or you can slice it in a way that has little space-time chunks, like a month of Wisconsin, okay, and that's ravioli slicing, right? So you can interact with these zarr arrays, not in the same geotiff or netcdf, endless data slices format, right? It's meant to be more multidimensional data format that has this kind of commit functionality where we can do replacements. So, what's the best weather forecast to use, and how do we forecast ecosystems? I'm not the ones to tell you that there are a lot of AI-enhanced weather forecasts now, and there's a lot of conventional weather forecasts, and they're getting better and better all the time, and we can do so much. So this is GraphCast from Google DeepMind back in ancient history in 2023, okay? And ever since then, it's like every time I turn my head, it seems like I was writing a grant with Encore, this is what I'm thinking about, right? And so writing the grant, it's taken me, like, over the summer, it's taken a couple months, and like every time we're going back over the methods section, there's like another AI-enhanced like model to use. It's like the next and greatest thing. And it's getting overwhelming, and it's, I don't know. I know that they do well, I know that they have their challenges, and I know that conventional weather forecasting is in many ways just as good or better, but there's a lot to do. The problem is we can't really forecast ecosystems in that same way. Because weather forecasts rely on knowledge of physics or your AI-enhanced projection and your initialization. That's really important. For ecosystems, they have memory, but not in the memory of the sort that we think. Let's say you're somewhere and there was a drought last year. Well, what did those plants do? They probably grew their roots deeper. Okay, they probably searched for that water more. They changed their fundamental structure to account for that, and that change in their structure is going to impact their current and future behavior. Right? So there is an adjustment that they make, an acclimation we call it, to how the past worked, with questions about how much of that information is necessary to forecast future behavior. Right? If you've seen a drought before, are you going to be more resilient to the next drought? Right? Quite possibly, for many different reasons, including the fact in my little root example. It could just be you changed the vegetation type to more drought-tolerant vegetation in the first place. So there's all of this baggage from the past that impacts what's going to happen next. We can't just simply initialize, and we don't have the observations anyways. Right? We can do our best to have a forecast with uncertainty that we can fuse in a Bayesian way with another forecast and come up with a new best estimate and go forward with that. Right? Or perhaps, at least for these medium range, like kind of up to 2-week forecasts, maybe we can do things in a very similar way to how our AI-enhanced weather forecasts work. Right? Maybe we can take a graph neural network, which is how WeatherNext graph works. And this is a really simple example that I showed because I can understand this of a graph neural network. It's like, okay, this happens to be for traffic forecasting. But things next to what's happening are impacting things. Okay? And if you have that information, you can build a model that can integrate everything together, right? But does that have sufficient information about how ecosystems work and their state? Or do we even need an ecosystem model? Can we even do this empirically? Or can we talk with our really smart colleagues? This is a figure from Chunying Huang, and she's in geography, who's working with us on trying to find like the most up-to-date and advanced sort of AI methodologies for understanding how to forecast ecosystem behavior. So this is a SWIN UNetR architecture that she's proposing. I fundamentally don't fully understand it, but that's why we work with Chunying, where we take our input, right, all these like encodings and decodings over time, and you're merging patches, and you're transforming, and you're retransforming, and I barely know what that means, and then you're going back, and then somehow within this transformer, a lot of things are happening. Right? But do we still, like, what's the most efficient way to kind of grab that past information to make a future prediction? And I still don't really know. Right? So I guess, right, at the end of the day, right, we're still in this state where we are writing grant proposals to find the thing to plug in here to be like you, right? To forecast ecosystems in the near term to try to help farmers with their irrigation, to try to help land managers plan events, to try to understand how ecosystems are responding to extreme events, right, and to get a better and more nuanced knowledge of how the carbon cycle and the water cycles work. We have ideas about what to do. Right? I know you have better ideas than I do about how to and like what best weather forecasts to use to do so. Right? But I guess at the end of the day, ecosystem dynamics are a little bit more of a bear. But I'd like to think that with a combination of knowledge-guided machine learning, all the observations that we have, right, and some careful forecasts, we can probably do this. So that only went about 40 minutes, and I hope that that's all right with you. I'd like to thank so many people again. Sorry, this is not formatted now. And our live data, I can give you some training examples if you want to work with it. It's all just on Colab. I'm going to use it in class for those of you who are in class in a few weeks from now, so you can start playing with it. And thank the data scientists, data providers again. Thank the colleagues again, and thank you again for coming, and happy to take any questions.
Time for questions, and by tradition, we like to have students.
Thank you, Professor Stoy. My question is related to the zarr array and the future array commit. I was just wondering what that process looks like. Is it like somehow combining the observed observations in the future array to come up with a more comprehensive answer, or how does that work?
So what it can do, in effect, is that this library, I can show you on Cyber, I don't think I have Cyber. This library lives like on the cloud. It lives in its S3 buckets. Like every one of these slices, right now we have it lasagna chunked. So every one of these slices has kind of like a big, long, crazy name. Once we start creating our future arrays, there's going to be like another block of data that the user, because of the metadata, is going to know as a future prediction, right? What we can do is once the real observation comes in, once our her data and our goes data and whatever else data we're putting into Alive creates through this, right, a new prediction, we can slide that into our library. And because of its commit history, it'll still know what that future prediction was. So that's kind of how I'm visualizing it. And also, right, as that prediction gets closer in time, you're going to be able to get a revised prediction that does better. Right? You don't always have to be like forecasting 2 weeks out and then like waiting. Right? So we can have our update occurring, and then our system like building that new knowledge into the same library. So this is how I'm visualizing that happened. Obviously, we have some ways to go to kind of think about like basically how we forecast the ecosystem attributes that we're using to create the carbon and water forecasts. Right? I think the weather forecasts, I mean, we're just like overwhelmed with possibilities. And we have our colleagues, we have close colleagues who do ecosystem forecasting, and they do really great work. But I think that their approaches, they take a very fundamental Bayesian standpoint about how to integrate all these things. It's just going to be a little too slow to be able to make like real-time predictions. Okay, and that's one of the reasons why I'm leaning pretty heavily into these AI-enhanced land surface attribute predictions instead of the traditional, what I'm going to call like an ecological forecasting mindset, where you're taking your data with uncertainty and you're integrating those things in this beautiful Bayesian math to come up with a prediction. Right? It's just going to be too slow. So we're trying to find like fast ways to do this. And then, yeah, in class in a few weeks, we're going to start diving into zarr arrays. But maybe I'll even have people like create them and make these kind of commit statements to be able to make it live.
So is ice chunk kind of like a storage place for both the future array and the zarr array then?
So the object storage buckets are where they're stored. Ice chunk is the thing that used to be called Array Lake by Earthmover, and it's just the engine behind Array Lake, really. It just provides the metadata for the user to be able to interpret what the zarr array is. And as a part of that metadata, right, that's where that commit functionality can come in. Okay, right, you can add to. Right? And so your system just has to say, okay, new observable, right, changing all the futures based on the new forecast, right, and then everything will just get like attributed correctly, hopefully, right, by the metadata service.
Yeah, one way I like to think about it too is those are support a lot of SCF formats, fine, right? It's a three-dimensional object storage. It has grids, and you can still slice it in that same way, but it's pretty static, and updating is challenging. And what's nice about zarr is that in your pasta analogies, spaghettis, raviolis, and lasagna all take pretty much exactly the same amount of time to extract, which is actually very, very, very difficult in SCF files.
Yeah.
Right? And that's really nice for those of us who want to do time series analysis, for spatial grids.
Yeah. you'd have to rebuild in that CDF, and ooh, that can, I mean, again, totally do that. That's just like a bit of a limitation. But to me, the challenge is like right now, because we're lasagna chunked, you'd have to re-chunk the whole thing to be spaghetti or ravioli. That doesn't mean you can't. I don't know. We're doing one thing at a time, basically, with our thing. But in principle, you can do that, and it's really quite powerful. They're having a big conference in Rome, like right now. I'm always getting their updates and or Earth Movers updates and people who are working in zarr. But it's pretty cool. Yeah.
Yeah. So regarding the inputs to your model here, you're using a lot of like pretty raw information. I think you've given good reasons for why you're using it.
Uh-huh.
Because you know that they're related to the outputs that you care about. But I also wonder if you had another model that you just trained on a traditional atmospheric model, but you still trained it on, hey, I want to know what these values are in the future, but just use these atmospheric inputs from existing models. Like, would that model do as well, which might tell you that there's not that much more information here, or would it not do as well, and then you know that these specific values are giving you more information? Has anyone tried that?
Yeah, not yet. So that's kind of what we're proposing to do, is like a benchmarking framework to interpreting what the actual innovation is. I mean, honestly, as much as Swin Unit R sounds really cool, and it comes from like medical sciences trying to find cancer in the series of imagery. I mean, this is very important stuff. Mm-hmm. And they're kind of, that's like what this is all ultimately is like kind of part of its genesis. Is this just going to be too heavy to be useful, or like is like a fundamental like CNN LSTM going to be best? But the CNN LSTM, we don't know how far back to go, and the graph neural network doesn't really go back that well. So there's sort of we need to do a lot of like kind of fundamental benchmarking work. And you make a really interesting and important point that I didn't go into too much detail about for here. So all the way back to here, we were using a lot of raw top of atmosphere reflectances and brightness temperatures for, where are we? I went too fast. Here we go. For here, right? These are forming the basis for our own like in-house DSR and LST models. Another thing that we've found out, and Sadeg's written a couple papers on this, and this vegetation indices one, the machine loves the raw data. As soon as we start giving it something that we've kind of poked about and manipulated, it doesn't like that as much, and it will quickly find the right connection based on the raw top of atmosphere reflectances alone, which is not very satisfying from the standpoint of all the interesting atmospheric attenuation and physics that's happening between the satellite and the surface. So it's just what the machine likes. The machine just likes the data. It's super starving for data. Mm-hmm. So that's why that's taking place. The reason that we're creating this kind of NARVP is just NDVI multiplied back by near-infrared reflectance. It's way more related to photosynthesis than you ever think it should be. Super related. We've also added shortwave infrared reflectances at 2200 nanometers to this, but not the one at 1800 nanometers, because that one at 2200 nanometers, which is band 6, the machine loves it. So it's really hungry for that band and the shortwave, and this has something to do with water, but like Mikan taught me, there's like the Optram model, but I don't know if it's the soil water or it's the canopy water or if there's something else entirely, including some of those like nitrogen bonds that are also active right around there that have to do with like plant nitrogen and like photosynthetic enzymes. So don't really know why it works, but it loves it. Okay, so we just do it. We listen to the machine without being slaves to the machine, hopefully. And yeah, we've kind of, now that we're integrating the HER, we're sort of stepping back from including those things, just using our surface reflectance bands and then relying on our meteorological data from meteorological data products. Mm-hmm. Super good question. That's another. Who's first?
When you were talking about raw data, is that like truly raw, like no normalization? It's just sensor data and it goes in and get a result, or is there some like by raw do you mean there's no like feature extraction or?
No, there's no feature extraction. It's just the top of atmosphere brightness temperatures and radiances.
Right.
So the brightest temperatures and reflectances.
The pure data, and then just in whatever value it comes in from the sensor, that goes into the model.
Yeah.
is there a fear of like overfitting to magnitudes of certain values?
Yeah, there is. So SADEG did quite a bit of like the leave one out cross validation and the training testing set comparison. And through it all, even though we're using a lot of bands for these predictions, so the downwind short radiation land surface temperature, including things that are not directly related to land surface temperature, they have to do with the cloudinesses that happen to impact the land surface temperature, including like it loves the ozone band. Because I know a lot of people study these things. It loves the ozone band. It just thinks it's like the best thing, which is probably telling us more about like weather systems moving through than anything else, but it knows that that means something, and so it assigns importance to that. And we have the whole SHAP analysis for what that's worth. But yeah, SADEG has gone through and we're really focused on creating these like light models that work very quickly. And we have colleagues in Germany who do sort of things like this, but at a more global scale. Not trying to do real time, but just trying to do machine learning upscaling. They also find that the gradient boosting regression, it just can't be beat. I don't really know why. It's not a super satisfying answer, but the machine likes to think of that architecture when it's trying to solve this problem.
I think one thing, if you didn't notice, right, all of the images that Paul showed were completely wall-to-wall. There were no clouds. Right?
Yeah.
So part of this is that
Oh yeah.
by training on the top of the atmosphere, you're actually kind of learning how to see through clouds.
Yeah.
Which is
Yeah.
pretty amazing.
These are all sky.
Which I didn't believe until
Yeah.
it actually worked.
Yeah, but then like physical models were developed here in the building of like all sky variables for DSR. The reason that we moved away from those, ironically, was that they were every hour and they had a coarser spatial resolution. And we thought it'd be easier just to have everything at the native spatial resolution and temporal resolution for alive. And now we've kind of stepped back to hourly, and I mean, when you do our comparisons here, this is the radiation. There's like a lot of differences, like right along cloud features, between our more spatially resolved like DSR and the one that's provided as a product by the GOES mission. Yeah, and both, hopefully both are great, but we just wanted to do our own thing. Question?
So it's my understanding that you're then trying to forecast hourly out to 15 days.
Mm-hmm.
So
Perhaps.
That, obviously your limitation, at least to one level, is the weather forecast.
Mm-hmm.
So then who do you see as the stakeholders with the end goal of the product, and at what time step do you think they'll get the most use from this?
Yeah, so boldly, I think we can basically predict flash drought. I think that that's a hugely optimistic statement, but I think if we combine what ecosystems do, and if we know about if it's going to rain in the next 15 days, we can probably effectively figure out that soil moisture decreases, like Jason Hawkins says, like so much per pentad that would result in a drought scenario. And the problem here is false positives, of course, right? Tell people, perhaps ahead of time, that this is happening. Something that I worked on in the past a lot was the flash drought of 2017 in Montana. And we're looking at sort of convective precipitation likelihood frameworks and seeing that well ahead of when the drought was declared, it really isn't going to have convective rain. The atmosphere is just too dry. But then the official forecast said, oh, it's going to be a great normal year, maybe slightly better than average, no big deal. Okay, so I'd like to think that there's some antecedent knowledge in the hydroecology of these systems that we can perhaps give warning about. I don't think we're anywhere close to being there yet, but I think that we can. And what we're trying to write the USDA proposal about, which I sent to Ankur like yesterday, the day before, and it's nowhere near in good shape yet, and we've got some work to do, is irrigation forecasts. You can tell farmers pretty well ahead of time, like if they want to or should start thinking about irrigating. And you can also tell them maybe the day of, but maybe they're on vacation. I don't know. So something where it involves like advanced preparedness for things that we probably can predict better than we currently are. Question?
Yeah, Paul, really interesting. Related to Grant's question, But on the other side of the coin, when we started making weather prediction in the 1950s, we ended up learning a lot about how weather systems work, by the challenge of trying to forecast them. So it was a hand-in-hand iterative process to learn more. What do you think will be the leading things you might learn about ecosystems by trying to predict them on shorter scales?
Oh, yeah. So going back to like the knowledge that we're trying to be guided by, I'd like to think that we need to know a lot more about the topic that I was just talking about. It's like kind of how fundamentally ecosystems respond to water stress. And the more we know about how water enters the atmosphere through ecosystems, the more we get a handle on that. And that's one of the big reasons why we're kind of focusing our early knowledge-guided efforts. And these are kind of these transformer models that are given hard and soft rules about what it can and can't do. And so by kind of learning more, right? And this is a project that's currently funded by NSF. I'm going to go to here, right? If we can see how much dew is rising from ecosystems across the U.S. in real time, that's not going into the soil, that's not going into vegetation fluxes. If we can see after a heavy rain event, right, how much more is going into the soil and increasing soil evaporation, or how much light rain events are entirely captured by the canopy, including this morning when I walked to my garage, it was completely dry, but the ground is wet. Right? This can teach us something, in fact, perhaps quite a bit, right, about how something as important as the water cycle is working across ecosystems. So my answer kind of always goes back to water, but that's also a naive answer because I'd like to hope, like you're saying, is that we can learn something even more fundamental about carbon cycles or water cycles or other things that ecosystems do, right, by tackling the forecasting challenge. But we're about 50 years or more behind you guys. You got to give us a little bit of time to catch up. We're trying to get there. And this may or may not be the way to do it, but I'd like to hope that it's certainly been interesting. So
Yeah.
it's been fun. Thanks for the question. Other questions? Yeah.
This is a naive question. So you mentioned that you're planning, or it might have already happened, applying this to the entire array of geostationary satellites. I'm curious on, in the regions where these satellites overlap, is there any potential benefit to adding channels for both, let's say, those east and west?
Yes.
To get both a western and eastern perspective to the same scene?
Yes. The answer is a strong yes, and it's a really good question. My data scientist, Danielle, who is fantastic, she just started a PhD at Boulder. She was really interested. She's really interested in fire, and she worked with Sam Vastley here in SSCC for a few years. And she wanted to kind of combine both view angles to get a better view of like each side of the mountains and things that that you can stitch together because there's a pretty substantial region of overlap, right? Especially around sort of the western United States. So that can happen, absolutely. So the thing about this is because of federal investments, the part of the United States, which currently is not working that well, unfortunately, right? We have an unbelievable legacy, things like the SSCC and other things, right, that have all of these amazing algorithms that create all these data products that when I'm reviewing papers or reading papers from our colleagues, right, we also make amazing investments and do amazing research, you know, in China and Korea and Japan. They don't have like land surface reflectance products. These are created to support the albedo algorithm from GOES. They just don't have a lot of the things that we have because of these investments, and so they're catching up fast. Right, have this kind of more legacy of research, and it's kind of building out this way. And then over here, from the UMetSat perspective, they've had geostationary satellites for a long time with Severi and other things, but the new Meteosat 12, sorry about the typo, is the one that has more like spectrally similar to what we're working with now. And going forward, there's GeoXO, who people in the building are very much working with. That's going to be even better spectrally resolved and better spatial resolution as well. So hopefully going forward in the 2030s and on, we'll have, you know, even the next best generation of sensors where we can kind of continue to build this like real-time and forecasting legacy.
Any questions online? Okay, so we will
No.
let's give another hand. You know where to find them. If not in our building, then just on the other side of Henry Mall.
Yep.
So
Thank you guys. Thanks so much. Appreciate it.